Yesterday's thermal conductivity instruments typically limit characterization to a narrow range of sample materials. The samples are often forced to adapt to the instrument's rigid requirements, rather than the instrument adapting to the sample and application needs. Trident, by industry leader C-Therm, represents a new paradigm in thermal conductivity measurement, delivering 3 of the most powerful transient methods in one instrument. It's better to have options. Built on C-Therm's reputation for world-class thermal conductivity instruments, Trident is dynamic and satisfies the most prominent ASTM and ISO industry standards. It combines the precision of MTPS with the flexibility of TPS and the robustness of TLS, all in one modular package. These options support a wide range of applications without sacrificing ease of use. Trident meets the needs of today's labs and is future-proof for the challenges of tomorrow. The MTPS, Modified Transient Plane Source method, employs a single-sided sensor to directly measure the thermal conductivity and effusivity of materials. The method features the highest precision and sensitivity, providing accurate test results in seconds. It offers the maximum versatility for the non-destructive testing of solids, liquids, powders, and pastes. It is adaptable for high pressure, broad temperature ranges, and environmental conditions. No regression analysis is required. MTPS is the choice method for situations where reproducibility amongst multiple users matters. With a double-sided sensor available in different sizes, the Flex TPS Transient Plane Source method provides researchers the greatest flexibility over experimental parameters, including timing and power. It is recommended for more experienced users with specialty slab, anisotropy, and thin film modules available. With no contact agent required, the hot disk-style TPS sensor is ideally suited for polymers, compacted geological samples, metals, concrete, and asphalt. Flex TPS is ideal for experienced researchers looking to push the boundaries in thermal conductivity. Sheathed in stainless steel, the TLS, Transient Line Source Needle method, offers maximum robustness in thermal conductivity testing. TLS is best suited for granular materials, polymer melts, soils, slurries, and gels. C-Therm software provides full data acquisition and analysis in one user interface, allowing full control of all 3 methods. Intuitive, logical, easy. Trident reflects C-Therm's years of experience working exclusively to provide labs, researchers, and manufacturers with the very best in thermal conductivity measurement. C-Therm's products are globally distributed in over 65 countries around the world, with full local support. Trident. It's better to have options.
Good day, folks. My name is Adam Harris. Welcome to our webinar. I'm just going to do a quick audio check here. Jacob or John, do you want to give me a quick thumbs up if we're good on the audio? Sounds good. Awesome. John Clifford, our marketing manager here, has helped organize today's session, and Jacob Pierce is helping moderate today. I'm very grateful for both gentlemen's help with putting on today's event. So I want to thank you for joining us. Our webinar application highlight this week is on specifically looking at high thermally conductive adhesives for battery applications. I'm going to be introducing this gentleman here shortly. I'm going to provide just a basic introduction before I do, but we're very excited to have an expert in the industry from Von Roll. Guillaume Gilbeau is joining us to talk a little bit about his group's work in developing conductive adhesives specifically for battery pack applications. I was in Detroit last week. I got a couple of different events focused on battery thermal management and innovations in battery packs. This is a very hot topic area, no pun intended. And exciting to be working with Von Roll and talking a little bit about how they're advancing the thermal properties of some of their adhesives and how they are well suited for this particular application and challenge, and how do we manage battery pack temperatures and optimize their thermal management for improved product performance and also safety as it relates to thermal runaway and some of the risks associated there. Today's webinar presentation should run approximately 50 minutes. We will reserve some time at the end for a Q&A session. If you have any questions as we proceed, please make use of the chat box. If we're not able to address your comment or question in real time, we will make a point of reviewing them in the Q&A session as well. We are recording. The link to the recording will automatically be sent to you if you registered for this event directly. Or if there's anyone you would like it sent to, you can also drop in an email address in the chat box. We'd be certainly happy to forward this on to any friends or colleagues that you think may have an interest in this topic. To start with, I want to provide a little bit of background on who C-Therm Technologies is. We specialize in thermal conductivity measurement, and our purpose in life is to simplify this measurement, to make it easier, more accessible to measure, so that you can have some support in your material formulation, your development. You're looking for quick feedback on formulation changes, and also in your material selection and validation of those materials if you're looking to incorporate them in a battery pack. So our purpose in raison d'etre is all about simplifying that thermal property measurement. We've done that with the launch of a new product a couple of years ago. This has been a huge success for C-Therm. We've more than doubled our sales with the launch of the Trident platform. Trident brings together three of the most significant transient methods for thermal conductivity measurement. We have the MTPS, which is that metallic, stainless steel cylindrical sensor on the lower right. This is the fastest, easiest way to measure thermal conductivity, very high reproducibility. You'll see this heavily featured in some of the work I know that Guillaume is going to present in a little bit. But we also complement this with a couple of other techniques which have their own inherent advantages. The needle in the middle is for really sticky situations. If you're dealing with a polymer melt, it's very robust. It's sheathed in stainless steel, so it's a very robust sensor and used a lot for analysis of materials in modeling plastic injection molding, for example. The yellowish sensor on the far left is a flexible nickel foil sensor that's encapsulated in a polyamide material. This is called the Flex TPS, or transient plane source. It's all about flexibility. It's a flexible sensor, but it's also giving you the flexibility as a user to iterate timing and power parameters to run more challenging applications like testing thin films, looking at anisotropy of a material. Anisotropy can be very important in understanding the heat transfer that happens in a battery pack, for example, where quite often the materials are oriented. They're through plane versus in plane thermal properties may be quite different. So really, when it comes to thermal conductivity, we suggest to have a few different options available based on the different materials that you'd be testing. And when we look at the anatomy of an EV, this is one of the reasons Trident is so popular, is because it's got such a range of different materials. You've got phase change materials. You've got thin films. Sometimes you have liquids for immersive cooling. You've got a lot of polymer composites, adhesives, and different pastes. So you've really got a pretty significant range of materials. You've got insulating materials like the battery separators, which are used to thermally isolate the different cells so you don't get that propagation. But then you've got other materials which need to have a very high thermal conductivity, like the adhesives and some of the materials we're going to talk about in today's webinar. So you really need a range of different solutions. So we advocate this toolbox approach. I really like this quote from Abraham Maslow. If you've seen any of my presentations, you know I use it consistently. But when all you have is a hammer, everything looks like a nail. And that really captures the value proposition to Trident. It's really about having the right tool for the job at hand. Because when it comes to thermal conductivity, you do need some different options. Now, how do you understand what method to deploy in specific situations? We've authored with several external colleagues as well, a collaborative journal on method selection for thermal conductivity. So this runs through the predominant methods, including traditional steady state methods, laser flash, and other techniques, and helps you understand where they're appropriate and where they are not appropriate to be applied. For example, laser flash is a very good technique. We have a couple in our lab. We use it a lot for high temperature ceramics or high temperature metals. We don't recommend it for composites because the anisotropy, the often heterogeneity present in a sample, can cause some pretty significant distortions in measuring laser flash. So it's a good technique, but you have to understand where to deploy it. And this is a good resource that's free to download if you'd like, just to map out kind of where the application and methods connect in terms of performance. All right, just before I introduce Guillaume, I'll just leave you with a client testimonial. We have a link, I think, in the chat here that Jacob will drop in on a wide range of different client references. But it's always good to talk to actual people or hear from people who are using the product and understanding, you know, does it do what it says on the tin, basically, I think is the expression goes. And we've got a lot of different testimonials. You can check them out. There's some from NASA, 3M, Intel, all kinds of different groups. But this is a really nice one from Sam Plunkett's group, formerly Allcell. Allcell was acquired by Beam Global. But Sam does a great job of kind of summarizing the value proposition of Trident, talking about it as a great instrument. We are able to look directly at thermal conductivity quickly, phase change composite materials for lithium ion battery packs. There are no special coatings required with the system. It was half the price, and it is really easy to use compared to traditional LFA. Sam goes on to call it a triple win. We use it weekly in characterizing our material. So a really lovely statement from Sam. I'm very grateful to Sam for sharing that, and just an example of a typical customer experience with C-Therm on the Trident system. Okay, so with that said, that's my basic intro. I'm going to invite the star of our show up to join me on screen. I'm going to stop sharing. Guillaume Gerbeau has 17 plus years working with Von Roll. I believe he started out in the R&D space and has migrated over his career to working more and more with customers as an application engineer, specializing in conductive adhesives. We've done, I think, one or two of these sessions before. They're always excellent. I love collaborating with Guillaume and really grateful that he could join us today to share a little bit about some of the work that Von Roll is advancing in this space, particularly related to battery pack design. So with that said, Guillaume, I'll pass the baton to you and I'll rejoin you at the conclusion.
Thank you, Adam, for this introduction and to invite me also to present our last development. And so good afternoon to all. I will introduce you how we developed our last conductive adhesive, high thermal conductive adhesive mainly for battery application, and why also we choose the C-Therm equipment to manage our development. So first of all, I would like to introduce you shortly our company. So Von Roll is a long-term experimented Swiss group, so established in 1803 and with a headquarter in Switzerland. So as you can see on the map, we are very worldwide distribution with several production plant in each region of the world. So Europe, America, South America, India, and Asia. We are today around 1,000 people working in this company, and we are able to distribute by our networks our products in more than 80 countries with under, I would say, two main brains, so Van Roll 1, and you will see also Dolls 1. And we are expert in, I would say, high voltage and low voltage. I will show you afterwards. So I would say that our expertise is based on three main pillars today. So first of all, and the historical one, is the electrical insulation. So where we are able to provide solution and products for high voltage application like big motors, generators, but also for low voltage application like industrial motors, for example. The second one will be the electronic protection, where we have different range, I would say, of product from impregnation to potting resins to provide solution for the electrical protection of the parts, but also of the machine. So you can have, for example, PCB protection, conformal coating, potting, and all this kind of stuff. And the third one is the composite range. So there we have a ready-to-use solution for a very wide industrial application. And as we will speak today about battery topic, we have, for example, we are producing cell spacer based on mica technology, mica for so the battery separator to avoid thermal runaway inside the battery pack. So here is I would say, if we focus on Europe, is a really quick overview about our competency centers. We have also some competency centers in USA, for example. But here we have mainly in Switzerland a focus on high voltage topics, where we built very recently a heat drive lab where we can manage really huge testing, focus on, I would say, driving automotive application. Very close to that in Switzerland, also a high voltage lab where there is, I would say, the huge knowledge and the long-term experience on Van Roll. And we have also application lab where we have facilities and huge range, wide range, I would say, of equipments to help our customer to go quicker and test our products and go quicker to the solution. So for there, we have some application lab in Switzerland, in Italy, in the Torino region, and in France, where I'm located, so in the Lyon region. And in all this lab, for sure, as we are chemists, we have also huge, I would say, equipment, wide equipment to measure mechanical, analytical, and also chemical properties of our products. And there we can also make some assistance to our customer. If we focus more on automotive applications, so we have solution for, I would say, the full cars application. So starting from the e-motor, for example, electronic control unit, cable joints, sensors, inverters, all this pack, and what will be the topic today, the battery application. So today on the market, I would say that we say three main cells type for this battery, so cylindric, pouch, and prismatic cells. And I would say that our resin and our adhesive will act at three different levels of this battery conception. So at the cell level itself, as I will show you just afterwards, at the model, but also at the pack level. And we provide solution for the three main type of cells that we can see today on the market. So first, I would say I would like to focus on what is called self-leveling adhesive. So you can also hear potting adhesive. So those products are low viscosity adhesive that will have the capacity to flow like a potting resin. And it will be a very good combination between the fixation of the cells by the mechanical fixation and the gap filler, I would say, efficiency. So it is a kind of 2-in-1 product. So you will need to have additional gap filler to make the transfer, the heat transfers from battery pack to the cooling system. This product has to be very resistant to shock damping and also thermal shock that I will show you after also. And this allows to have a very homogeneous heat dissipation by the fact that you will have the product everywhere around the cells. This could have a positive impact on the battery lifetime. This kind of product could be used so at the cells level, so for the venting cap protection, and also I would say the mechanical fixation of the bonding wire. And it is also a barrier against the corrosion of the top of the cells. It could be used in another design as the bottom part fixation. So in this case, you put some centimeters of resin on the bottom part of your pack. And sometimes you can see also other design with a full potting, in this case, application, where there you put resins all inside the battery pack, and that you're covering all the cells with the resin. So for this application, and also a little bit for the thermal adhesive that I will go for the afterwards also on that, we developed our Damival series. So this is a unique backbone based on polyurethane chemistry. We call it next generation polyurethane because it is using a CMR-free solution. So it's no carcinogenic, mutagen, or reprotoxic substance inside. It is also without silicone, but we can go to very high temperature resistance, usable to up to 150 degrees. This is very elastic material because we can go up to 200% of elongation. And as you will see also afterwards, this is a product with very negative glass transition. So it means that it will be very resistant to thermal shock because usually in the automotive, we see the range of thermal shock starting from -40. And in this case, the glass transition is -55. So it means that also at -40, you will have very flexible and soft materials. And for sure, this has wide range of approvals, like for the railway EN 4545, or for also the UL 94V0. And it is already used today, I would say, by one of the main and the biggest battery supplier worldwide. So what we call the next generation technology. So the first topic really important is that, as you can see on the label, for example, if we compare today our next generation system and the market reference, we don't have this TMR label. So with the guy with the bus irradiated. And this provides also other advantage. So the first one is that this technology is less sensitive, I would say, to humidity and storage conditions. So it means that you can have a better storage lifetime and less influence, I would say, on the main and very important parameters, which are reactivity and viscosity, which could be impacted time by time by this humidity attack. Those solutions are very easy to use, and we already tested and approved this with several suppliers and several partners with both technology that we can see today on the market for dispensing equipment, which are or a static mixer or a dynamic mixer. Our star product, I would say today on this range, is called Damival U602. So this I choose to put some, I would say, to highlight some very important parameters. So this is a very easy to use product, very versatile potting material, which has good adhesion. I will also present you some data afterwards on some challenging substrates, and is very flexible and elastic product. So as you can see on the tab, there is a good balance between the viscosity level. So here at 25, we are on the mixing viscosity around 4,700 millipascal. But also you can see after that it is by playing with the temperature, we can easily decrease this number. The glass transition temperature, as I told you, is very negative, -50. So it will give a huge flexibility on this product and a good resistance to shock and thermal shocks. And we reach a thermal conductivity level around 1 watt per meter Kelvin. This product has wide range of homologation behind, and for sure is supplied to the REACH and is compliant, to REACH and RHS level. I forgot to tell you that this product, I would say the potting self-leveling adhesives are used only, I would say today, for the cylindric cells type. So on this product, we ran, I would say, a lab scale thermal run array just to see what happened and what is the effect on this self-leveling adhesive. So I would say at T0, we insert a nail inside a full potting design battery pack. And to initiate the flame, and I would say to start this thermal runaway. So as you can see on this picture, after only 3 seconds, the flame are extinguished by the product. And you started to create hot gases. Between 10 and 50 minutes, you achieve the highest peak of temperature inside the battery, which is around 120 degrees. And after only 30 minutes, the temperature starts to slow and to decrease to reach around 40 degrees after 50 minutes. So with this, I would say, lab scale test, we can easily see the efficiency of this product and the impact first on the stop of the flame, extinguish of the flame, and then afterwards the dissipation of the calorie through this resin. So here is a picture with a comparison before and after the thermal runaway. So what is highlighted in red is the part where we were forced to remove, I would say, a resin to insert the nail for initiating this thermal runaway. And you can see that even after the test, the design and the resin stay safe. And there is no damage, no bubbling, no, I would say, deterioration of the resin. So it's very resistant, I would say, to heat and fire. So why the thermal runaway was so slow down, I would say, in this case? First of all, for sure, this is a full potting design, so there is a lack of oxygen below the potting area. So in this case, there is no access for the flame to additional oxygen. And additionally to that, you had the fact that this resin is self-extinguished, so it is UV resistant and fire resistance. And also this, I would say, thermal dissipation, homogeneous thermal dissipation in this case, because for the full potting, you have the dissipation on all the way from the back, the bottom, and also the side. So it helps also to dissipate the calories, the heat, and go this test in a safer way. Here, as I told you before, so there is a big impact, I would say, on the process condition on the result that you would like to achieve. So here I choose to highlight, I would say, two main parameters. So first of all, the impact of the temperature on the viscosity of the product. So here, this is based only on the part A, but you can see that for around 7,000, 8,000, I would say at 25 degrees, you can reach, for example, 2,000 at only 50 degrees and close to 1,000 at around 60. So by playing with the temperature, you can decrease very drastically, I would say, the viscosity. The other effect of the temperature and the process on another parameter is on the reactivity, and so the polymerization, I would say, on this product. So here we choose to compare on the same product two different temperature. So 25 degrees and 50 degrees. And you can see that at 50 degrees, you achieve the final hardness, I would say, of the resin after only 5 hours, when 24 hours is needed for 25 degrees. So you really accelerate, I would say, the polymerization. So by playing on the temperature, and with this product is possible as to 100 degree, you can easily play also with your process and accelerate as if needed in your application. Next topic is the adhesion properties of this Damival U602. So we tested on different, I would say, substrate, quite challenging. So in this case, first of all, with aluminum and polycarbonate, and we manage a lab shear test. So the important thing, according also to the result, to the level, is the profile of the break in this case. So for this kind of adhesion properties, the best is to have a cohesive break. So it means that the adhesion, I would say, on the substrates, the resistance is higher than the resistance of the product itself. So when it breaks, you still have some material on both samples that you shear. So in this case, the results was very good on aluminum and polycarbonate, but also on other, I would say, challenging support like polyamide, PBT, and so on, where we also see cohesive break in the failure. On other plastic like PMMA, PE, polypropylene, and so on, we will pay attention on that, and we will say today to be tested case by case, because it could also depend on if there is some surface treatment or other things to manage before putting this adhesive on the top. Next topic, and very important, is the thermal aging behavior of this system. So here we choose to, I would say, test this thermal aging with two main test we see in the automotive market. So first of all is the thermal cycling, where you go from 75 to minus 45 with different cycling, different ramp. And there, after 500 cycles, we had only 0.3% of weight loss. So it very resist to this test. The second one is the thermal shocks. So very important test where you go generally in the battery field from minus 40 to 60 degree, plus 60. And there also, as the temperature is quite low, we only reach 0.02% of weight loss. And to really show the good thermal resistance of this system, we choose also to make, I would say, a weight loss test at high temperature, so for 1,000 hours at 130 degrees, sorry. And as you can see on the graph, the results is that the weight loss is below 5% after this 1,000 hours at very high temperature. So we can easily conclude that this material is very resistant to temperature. So additionally to this U602, we developed other, I would say, thermal interface materials, safe-living adhesives with higher thermal conductivity. So this product is also based on polyurethane chemistry, in this case, also CMR-free system. And there we achieve good results by well balancing also the viscosity. So in this case, at 25 4,500 and reaching a higher thermal conductivity, and then we reach 2.0 watt per meter Kelvin. We have also under development other product to achieve 2.5, 3, and maybe more in the coming months. And we developed also another, I would say, product. In this case, we are based on epoxy chemistry, so with pro and cons compared to polyurethane. Really, the pros is that you will reach a very high adhesion, probably also superior adhesion compared to the polyurethane. But we would like to keep this, I would say, flexibility for this application, don't have, I would say, the common rigidity of an epoxy. So in this case, we developed this Damival E101, which is a semi-flexible epoxy. And then also the target is achieved because we reach 1.5 watt per meter Kelvin in terms of thermal conductivity by keeping acceptable viscosity at 7,500. In this case, also by playing with the temperature, you can drastically decrease this viscosity level. And then we go to the second solution that we can see today in the battery field, which is called thermal adhesives. You can hear also sometimes thermal glues. So here we are not speaking about, as before, about self-leveling products. Here we are speaking really about thixotropic and very high viscous products. So as you can see on the picture, this is some product that you can apply by cords or by beads on vertical but also horizontal way, and it has to stay in place, I would say, and don't flow, don't drop, and really stay in place. So this is used, as you can see also on the picture, to glue cells together and also to make the thermal bridge between the cells and the cooling system of the pack. This could be used for the three types, I would say, of cells that we can see today: cylindric, pouch, and also prismatic cells. And we developed also in this range based on the same, I would say, spirit than the U6A2 we see before, with a 2K polyurethane system and flexible materials, because important topic also in this battery field is to be resistant to thermal shock and also to this mechanical shock damping. So our star product in this range is the Damival U620. So I choose some important topic on that, but this is also this product has a good adhesion because it's based on the same backbone also at the U602. So this has a good adhesion on several and very challenging substrate. This is quite easy to use. It could be, I will show you after that we made also some industrial test with one of our partner, and it is really easy to use with different kind of mixer, and in this case also with static mixer, with a mixing ratio is a 10:1. This is again a 2K formulation, so you have no solvent, no additional solvent inside. So 100% of the product that you will mix will be used. And in this case, we achieve 2.4 watt per meter Kelvin in terms of thermal conductivity, with, again, as we are on the same backbone, a glass transition temperature which is very negative, minus 65. So it means that also at very low temperature, very negative, you will stay soft and resistant to shock and shock damping. So on that, we manage also, I would say, a lab scale test. So on some cells that we can see, some reference cells that you can see on the market. And there, so we glue those cells to an aluminum pack, I would say, to an aluminum substrate with this adhesive. And then we started to heat the cells. And we recorded time by time, so after 10, 20, 14, 15 minutes, the temperature, so with a camera. And you can see that with the U620, you started to dissipate, I would say, the calorie quickest than, I would say, the reference that we take in place, so which has a lower thermal conductivity, and that we can see today on the market. And that at the end, you can see that the blue parts, which is the coldest one, grow very fast with the U620 when it's still hot, I would say, on the right with the market reference. So I would say that this could result, this thermal management and this help to dissipate the calorie could result in three main, I would say, advantages in battery feed. So to have safer battery, because the coldest the temperature is, the lowest is the risk to have thermal runaway inside the battery pack. It could also result in higher efficiency because you can also put more power and more heat, I would say, because you will be able to dissipate in a better way this additional heat inside the battery pack. And this would be also reliable for high power density, because for sure you can increase the power density. It will increase the temperature, but in this case, you will be able to really well dissipate these calories. This at the start, I had the video, but it doesn't work here. But we made some trials with one of our partner, which is Bilitronic, is the German company, really specialized, I would say, in dispensing equipment. And there, so we made some applications, some industrial trials by using, as you can see on the left, some static mixer. With this mixing, and I would say, dispense this adhesive on cells to glue cells together, and also to see, really to show the thixotropic effect of this thermal adhesive. So as you can see completely on the right, this could be applied as a cord or bead, and it will stay in place and not drop or flow. It is also easy pressable, I would say, between the cells, so you will not need to really apply high pressure to really glue the cells and have a homogeneous films between the cells. So for, I would say, better idea on that, there are some video available on YouTube. So if you tap in the search bar Van Roll or Bilitronic, you will find also those videos, and you can see really the application of this thermal adhesive. Sorry. So in Van Roll, for all this development, we choose to use the MTPS method from C-Therm. So as Adam explained you today, what is this MTPS method? So we bought, when it arrives on the market, those Trident equipment that you can see on the left. And we are using today this equipment on two of our plants, so of our resin design plant. So one in Mezio in France, where I'm located, and the other one, our Italian plant. And I would say why Van Roll is trusting and choose to go with C-Therm for this development, for, I would say, four main reasons. So the first one is that this is a very robust method that we use now in Van Roll for more than 10 years. So we use now the Trident, but we were using also the previous generation of this MTPS method. And this gives very reproductive results. The second one is that with this method, you have a very fast results acquisition. So it allows you to really save time and money, in this case, in product development, because you will have really quick the results of your thermal conductivity. This is very flexible, I would say, method, because you can measure different kind of shape and thickness for each samples. It is also, there are some options, so you can measure also some liquid, and it is possible with an annex oven to measure also this parameter at very high or negative temperature. Just have to change the cooling, the contact liquid, and so you can play with the temperature. And also the last, I would say, big benefits for us is that with this method, we can easily see a settlement level indication. So for that, you measure the data, the thermal conductivity on both faces of their samples. And if you have a big difference between the top and the bottoms, it means that the fillers are settling inside your product. So this is very, very a very good information for us also to have this indication of settlement in our product. And I am at the end of my presentation, so thank you for your attention, and if you have any question, do not hesitate.
Excellent. Thank you so much, Guillaume. That was lovely. Great presentation. Really interesting to learn all about the development work that Von Roll is pushing forward and driving innovation in battery pack thermal management. We will have an opportunity to take some questions. I'll just ask you to stop sharing your slide deck. I just want to talk a little bit more about filler distribution. You touch on at the end there a really interesting point, and we've got some interesting work coming up here that may be of interest to folks in that area, with more of a manufacturing or production view on that issue. So I'm just going to bring the file up. So first off, folks, a few additional resources. If you're interested, please check out C-Therm.com. All of our webinars are recorded. You can actually find some of the previous ones Guillaume has recorded with us. He always does a great job, as you can tell. There's some good resources there. Also, the tech library. It's a searchable database of publications. A great resource if you're trying to learn more about some of these methods or the application areas where they're applied. So when we're talking about increasing the conductivity of an adhesive, any kind of polymer compound, we're typically using some sort of filler material. And there's a broad range of different filler materials used, ceramics like alumina, different types of like carbon nanotubes, multi-walled, single-walled, boron nitride. There's a broad range of different fillers that can be used in these types of applications to enhance the effective thermal conductivity. And there's a lot of work done to make sure that they're well distributed, but they tend, depending on the filler, they sometimes tend to agglomerate, or over time, as the material approaches its shelf life, you can get this settling that occurs in the material based on the different density of the material. Now, a well-formulated product will do a good job of maintaining that thermal conductivity up until its shelf life. But there's always this question as you go to dispense the material, particularly at larger volumes now that we're talking about electric vehicles battery packs, of how can we get some traceability or assurance that everything is in a good compositional state. So this is an issue that we've been paying a lot of attention to and having a lot of discussions with the OEMs, tier one suppliers, and the manufacturers of these materials. And really what we want to highlight here is what's changing in our space here is that the volume of material we're dispensing is increasing so significantly. So where we used to use these types of adhesives in smaller quantities on smartphones and laptops and tablets, now we're dispensing into battery packs that are often twice the size of our desks. So it's liters of material sometimes per battery pack. And then as that volume increases, so we're moving from like a dispensing gun to a pail to a 55-gallon drum, all of a sudden some of those issues around product stability and settling, distribution, sedimentation of the materials can start to become more significant. So C-Therm is looking for expressions of interest in this area. If there's folks on the line that are involved in scaling production processes for EV battery packs, we'd like to talk to you and better understand if sedimentation is something that's on your mind. You can drop a note in the chat box. We'd be happy to follow up with you. I'll leave you my email address as well in the chat box if anybody wishes to reach out. Be happy to talk about how we've applied our sensors, like the ones you see on screen here, in other industries for process monitoring in control. There's an opportunity to potentially introduce these at the point of dispensing so that we can understand confidently with traceability the consistency of those materials as they're being dispensed, ensuring that the filler is where it needs to be and as well constituted in terms of the product stability. So if that's of interest, we'd love to hear from you. There's some really interesting collaboration happening in this space. I see a number of folks on the line that are active in this area, so that would be a good opportunity to solicit some expressions of interest there. This is called an ESP sensor. It uses the same sensor chip as the Trident system. It's all based on the MTPS method, and there's a long history of these being applied in process monitoring and control applications in production. So we'd be looking here for fillers, settling, dispersion, homogeneity, product consistency, and also the potential to monitor for any kind of air entrapment. Get an air bubble in your dispensed material. This can cause a significantly reduced effective thermal conductivity. So if any of that speaks to you as an area of concern or interest, please do reach out. We'd love to learn more about the potential to collaborate in this area. We have a couple of webinars coming up, one December 1st, next week. It's hard to believe we're moving into December next week, but November is flying by. So this is just another customer of ours, MS Sleeps. Angela and Rogan will be joining us from Germany and talking a little bit about the work they're doing in thermal comfort and bedding. And then more related to my previous comments, we have another webinar the week after, December 8th, on inline monitoring of filler distribution and dispensing adhesives. So for anyone that's interested, that's a great opportunity to learn more as well. Please follow us on LinkedIn if you'd like to stay tuned of more updates from C-Therm and our partners, such as Von Rohr. We'd like to share any kind of news from our partners or collaborators that's of interest to our client base, which is a lot of OEMs and tier 1, tier 2 suppliers in this space. All right. If you're found any of that interesting and you'd like to book a discovery call or get a quick quote, it's that time of year capital budgets are being spent. If you would like some product information or a quote, please let us know. We can send you that information. And at this point, I'm going to stop the recording and we're going to review some of those questions. We got a bunch of really good questions that came in through the Q&A. But we'll stop the recording at this point. Let me just say before I do that, thank you very much. We hope you found this an interesting investment of your time. We really appreciate you taking the opportunity to join us online for these discussions. So on behalf of myself and Guillaume, a hearty appreciation and thank you for joining us today. Okay, so we're going to stop the recording here